Hi, everybody. We are now diving head first into this new unit. We're going to call it the Net Force Particle Model Unit. And this is stepping forward from the Balanced Forces unit from last week and before that. So, in those previous units, or the previous unit, we saw that under Newton's first law, objects will not accelerate unless there's an unbalanced force, and we get into free body diagrams and things like that. So the verbal description, the words, were just that, and then we got into diagrams. Those were the free body diagrams, and then we kind of sort of dabbled with some equations built out of those free body diagrams. So let's continue that with the next step forward in our words. Don't ask me why that yellow thing pops up. This is driving me crazy trying to figure out silly things with this program, like where did my eraser go that I used to have. So sorry if I get frustrated here and there. I know this is frustrating for everybody in a lot of different ways right now. So words. Newton's second law says an object will accelerate. So I'll just say, and this does write better if I go in cursive, I've learned, than trying to write in, what's the opposite of cursive? Print. So objects will accelerate. So you'll find me getting kind of like back and forth between cursive and printing, I think. So they will accelerate if an unbalanced force occurs. Okay, that other thing, remember the other thing or the other word is a net force. If a net force exists, then things will accelerate. The bigger the net force, the bigger the acceleration, and oppositely, the bigger the mass of an object, the harder the acceleration will be to make happen. And so we have F net equals ma, and sometimes that's rewritten to illustrate what I just said. If we rearrange it to solve it for a, then it becomes F net divided by the mass. So mass here, acceleration, F net. You saw some of that in the notes that you took the other day. So in any fraction in the denominator, if the denominator gets larger, then the value of the fraction gets smaller. So for example, if we had 10 on the top and 10 on the bottom, that 10 over 10 would be equal to 1. If we had 10 on the top and 1,000 on the bottom, then that would be equal to like 0.01. So the bigger denominator, the smaller the fraction. So that's what we mean by if the mass gets bigger, the acceleration is going to be smaller. And you know that from everyday life, trying to get heavier things to move, it's not as easy. And so that's mathematically why. So then when we go to diagrams, this is our free body diagram idea. If we had, before we had balanced forces, and when we had balanced forces, turn it into cursive. If we had balanced forces, it meant anything to the left and to the right would cancel each other out. Anything up, anything down would cancel each other out. So if those are equal, then these are examples of balanced forces. And acceleration equals 0. That was before. Now, unbalanced forces would be, let's say, you are going to get in your car and you're going to hit the gas and you're going to accelerate down the road. If you accelerate down the road, it's because your car pushes backwards with its tire, but the road pushes forward. And that leads to the acceleration. What the free body diagram would look like for that would look like this. We have normal force, we have gravitational force. The car does not accelerate up from the road, it doesn't jump up into the air, so those are equal. But here the force from the road, this is what I'm talking about, sorry about that. The force from the road on the tire is not being balanced off by something over here toward the left. Yeah, there might be some friction with the wheels in the road backwards, but the unbalanced force is occurring because there's not a sideways force back here to counteract the forward force. And how this would translate then from the equation at the top, F net equals ma, that's Newton's second line equation form. So the fact that the car is supposed to go in the x direction, if we want to call it the x direction, that's sideways. We'll look at our free body diagram and pull the equation that is sideways. So it could be something like force from the road. That's the only sideways force, equals m equals the mass times the acceleration. If the mass of the car was, say, 2,000 kilograms, if the mass of the car is 2,000 kilograms, we could put that in there. If we knew that the force from the tires on the road was, say, I don't know, 30,000 newtons, then we would substitute that in over there where the force of the road is, and the question might be, what is the acceleration of the car? And the way that we go about finding the acceleration of the car is using the free body diagram to identify what forces go on the left-hand side, and then substitute in the mass of the car and solve it for A. So if this was the case, if I had 30,000 newtons and the mass of the car was 2,000 kilograms, and we were looking to find the acceleration, then we divide, simple algebra here, by the 2,000, and 15 meters per second squared, remember our units for acceleration, would be our answer. That'd be a bit of a ridiculous acceleration for a car, but that's about how we would go about it. I'm going to kind of move a little bit more quickly, I hope, through these next couple of examples. While an elevator goes up and down and the car was going side to side, the process is 100% the same. Doesn't matter which direction that our forces are acting, the idea does not change whatsoever. So let's look at these questions here, and I'm hoping I left enough space on the diagram or the worksheet to work through this. So in part A, this is just like we did in the last unit. Force of gravity on a person is the mass of the person times g. What's g? G is that 10 newtons for every kilogram of mass in an object. So in this example, the person's mass was 70 kilograms. So remember, 70 kilograms is not 70 newtons. Newtons is force units, and in this case, We can't say the person's weight is the force of gravity, which is 70 kilograms, because kilograms is not a unit of force. So remember to pay attention to the difference between mass in kilograms and force, which we call weight, in newtons. So I plug in that 10 newtons for every kilogram for G, and the force of gravity on this person in an everyday sense would be 700 newtons. So going on to B. B says, what's the value of the normal force? This is where we start to use a free body diagram. What's the value of the normal force? So our free body diagram is a way to relate things like the normal force to the thing that will tell us about the normal force, and that's the force of gravity. So when you stand on the ground, stand in the elevator before it moves, the normal force is equal to the gravity. Why? These are equal because A equals 0. Now, we've just said it that way before, but the real reason it's that way is because of Newton's second law. So if we said F net equals ma, and in this case, we are just thinking that we are not even in the elevator, we're on the ground, not in the elevator, so we're not accelerating. That tells us that our acceleration is 0. So if F net then equals whatever your mass is times 0, this whole side would be 0. So now what do we do on this other side here? We briefly looked at this before. We would say the forces that are acting in the direction that matters here, up and down. So we would say the force of gravity plus the force from the floor or the ground, the normal force, equals 0. Okay, well, one of them's up and one of them's down. Let's call up the positive direction. Oh, let me hope that this doesn't change everything. I just wrote to a different color, and it didn't, like it does sometime. Let's say down is negative and up is positive. That means force of gravity would be the negative direction. This would be positive. So really what we'd be doing is subtracting the two. But if we go back to just kind of like saying, what was our goal here? Our goal was to figure out what the normal force is when they're standing on the ground. This is just an equation. We just figured out a second ago that the force of gravity was 700 newtons. And if that's that negative direction, we put the negative in front of it, and then our normal force, and that equals 0. Well, we could just rewrite this just like any algebra equation, move the 700 to the opposite side of the equation, and the normal force would be equal to 700 newtons. Notice it became positive when we moved it over there, and that is because up is the positive direction. So that's just the formal way to do what we were kind of doing intuitively before. The normal force is 700. If we go to C, the accelerator or the elevator accelerates now vertical upward. And it said that earlier in the question, didn't it? The elevator accelerates upwards eventually at the speed of 3 meters per second. So the speed goes up by that. So that's what our new condition is for part C. So now A equals 3 meters per second for every second, and that's upward, so that's positive direction, and that's important because if we were going to accelerate downwards, then we'd have to think about a negative sign, and that changes things quite a bit. So what are we looking for in C? We're looking for what happens to the weight of the person. So the weight is kind of like this force of gravity thing. And some of the work that you did already was kind of preparing you to think about the fact that you do feel heavier when this elevator takes off and goes up. You do feel heavier when you're on a roller coaster and you hit the bottom of a hill. You feel heavier when an airplane takes off. If you've ever ridden in an airplane and it takes off from the runway, you feel like you're pushed back in your seat or downward in your seat. Those are all perceived increases in your weight by your brain, because now your muscles are having to support a larger upwards force to hold you than it would if you weren't accelerating. So what do we do here? It says up here, always use Newton's laws to try to start your problems, and a free body diagram to go along with it. So now we've got the elevator accelerating upwards, so the normal force from the floor on your feet is still there, but I'm going to go off to the side and make a point to say the acceleration is up, and I do that because if that's the case, the upwards acceleration has to be bigger than the force of gravity down. I intentionally made the upwards force vector for the normal larger than the arrow for the bottom one. You need to do that. You need to see that that's important, because that kind of gives you a visual for which direction and why an acceleration might occur. So go back to the question again. The question was, what happens to our weight when we accelerate upwards? So we would say, well, what happens to our weight? Our weight is a perception from the normal force of the floor on our legs, and our legs say, wait a minute, that doesn't feel like I normally feel. It's pushing harder up on me, and I'm having to support myself with more muscular strength than normal. I feel heavier. So we're solving for this to say what happens to what we think is our new weight. So we go, I'm gonna run out of room if I go there. I'm gonna say F net. Whenever we have Newton's second law or acceleration, and we're dealing with forces, we should be thinking of Newton's second law in this F net equals ma context. So we have the normal force. It's larger, and that's going to lead to kind of an imbalance. That's what makes us accelerate. So we'd say the normal force up. I'm going to write that so you don't think it's somehow N for net or whatever, but what we're writing here simply replaces this starting point in Newton's second law. So we have the normal force and the force downward from gravity equals ma. That's a parenthesis that got out of control. So all of this just replaces this generic starting point for the F net side. Remember, we've got to think about directional stuff, so anything that is not in the upwards direction, up is positive, and down then would be negative. So this gravity, we'll put it in there as negative again. And from there we can start filling in numbers and get to our answer. So we're looking for how big is the new normal force. That's what we feel is our new weight, because of how hard the floor pushes on us. We think we feel different from that. The Fg is always m times g. This never changes. So it's negative because of the downward direction for the force of gravity. And so the 700 newtons that we found for our force of gravity up earlier in part A is still there. Now here's where you got to pay attention. The mass is not your weight. The mass is that 70 kilograms. I'm going to parenthesis that one so that we can keep the A separate from it. And the A, we know we're not calculating that. The A was going to be 3. Double check that. Yes, acceleration was going to be 3 meters per second. So that's multiplied, and now this becomes the normal force. That's going to be our new perceived weight, plus negative 700 equals 3 times 70 is 210. So now we move this over to the other side, plus 700 and plus 700. Guess it doesn't like it if I don't write big enough. So these cancel. 700 and 210 is 910. And those were newtons. It doesn't like it if I write too fast either. So there's our new weight. It's not a real thing, but it is a real force, and our brain thinks our weight changed because our legs are having to do more work to hold us up. So our brain goes, we just feel heavier right now. But as soon as the elevator stops moving or stops accelerating, then the force from the floor goes back to supporting just our regular old body weight of 700 newtons, and all is good again. So why does the person's weight appear to change during the acceleration period? Because the normal force is greater than the force of gravity, causing our acceleration. Oh my Lord, I am sorry that this is such a bad setup, but it's the best I got. I'm going to go back to writing in cursive because I told you a long time ago that that seemed to work better. Maybe this thing just doesn't like writing near the bottom of my little writing pad, but I'm going to start over. The force of gravity is greater than the normal force. Sorry, the normal force is greater than the force of gravity, and this leads to an acceleration upwards, which makes, and again, because that's bigger, our legs feel like they're supporting more weight. I have been practicing this, and it's not really, I'm not really as dumb as this looks. It is just kind of tricky. Your legs feel more weight, so to speak. So that's that question. We feel heavier when there's a larger force upwards from the floor than we're used to in an everyday sense. When you sit or stand, when you're not moving, then your body has a certain way of perceiving that amount of work it takes to hold you up. And when you accelerate upwards, all that upwards force is bigger than what you're used to. And that's why we feel heavier. In this is the last page here. But after any acceleration happens in an elevator, it does steady out and move at a constant speed for a little while. And when that happens, A equals 0. And we could go back to part B here at the beginning. So I'll just say C part B above. There's no acceleration, so the normal force matches your FG downwards, your weight downwards, and everything feels normal as if you weren't even moving at all. This goes back to Newton's first law. When there's no acceleration, forces are balanced, and you wouldn't know if you were moving or if you're at rest. Everything seems the same. So last question. A little quicker here because we don't have to go through A, B, C, and D like we did in the earlier part. But now we're going to slow down when we get to the top of our trip on the elevator. So now our elevator is slowing down. I'm going to make a little motion map. So your velocity is up, but you're slowing down. And hopefully you remember back from the days of worrying about the direction of acceleration from motion maps. If we slow down, then our acceleration points the opposite way of our velocity. So in this case, this acceleration of 2 meters per second says we should think of this, and down being negative and up being positive. We should think of this acceleration as being -2 meters per second squared. So now if we jump back, and I'm bored with blue and red, so let's play green right now. So if we were going to say how would our weight appear to change, it's the same exact process as we just did in the last question. However, the difference is we should feel lighter. So I'm writing higher up in my little pad and it seems to like that better. So maybe that's part of my problem with the bottom of that last page. So if we feel lighter, how much? Let's work that out. The answer to any question I ask you on a test or a quiz is not going to be you feel lighter, period, end of story. You'll need to say how much and why. So we'd start by thinking of it in terms of our free body diagram. Our normal force is not as large this time as our force from gravity. This is the reason why we have a downwards acceleration, so the downwards force has to be bigger than the normal force. So gravity's winning in this pulling, pushing match here, and we're slowing down as a result. So we go to our F net equals ma to get to the answer here. How much lighter? And these are just in the up and down direction. So we have normal force and gravity force and equal to ma. So we need to make sure we pay attention to signs like before. Gravity's down, so I'm going to say it's negative. And so now substituting in values, the normal force is this force from the floor that makes us perceive our weight. The force of gravity on this same person is still 700 newtons. The mass of the person is still 70 kilograms. And this time the acceleration is -2. Remember the negative because of the direction. You're moving up, but you're slowing down. So your velocity is trending towards negative. You have a negative acceleration. So we'll put that -2 in there. So this time the right-hand side, -2 times 70 is 140 newtons. And the normal force minus the 700. You can write it as -700 if you want to. You don't have to say plus negative, but we got to get used to why there's a negative in there. So when we do our algebra, our normal force is add the 700 onto this other side, and that gives us, oops, sorry, that's negative 140. So if I add 700 to that other side, take away 100, you get 6. Take away 40, you have 560 newtons. So how much lighter? If we it's basically that 140 newtons lighter. But we would think of this normal force from the floor as our quote-unquote new weight. So if you notice it, you might have said, "Oh, I see what's happening here." Remember, the net force is equal to the product of an object's mass and its acceleration. So in this case, it's saying our weight is going to change by whatever m times a is on the right-hand side. So our weight got lighter by 140 because of that negative acceleration here. In the previous example, our weight got heavier by 210. That was added on to the plain old normal body weight of 700 for this person. So that's one way to notice what's happening here. The unbalanced amount of force, so remember this is also known as the unbalanced force, The unbalanced force is really the amount that one is larger than the other one. In this last example here, the gravity force here was 700, and it turned out that the normal force was only 560, and that's what led to the slowing down effect. The unbalanced amount is 140. The net amount difference between normal and weight, or force of gravity, is 140. So we need to know that F net is the same thing as how much difference is there in the forces that are fighting each other. So we had some learning targets from earlier in the last worksheet that you did, and they were describe Newton's laws in words, describe mathematically how there's a connection between the net force and the mass and the acceleration of an object. Bigger mass, smaller acceleration, bigger net force, bigger acceleration. Diagrams, use these free body diagrams to set up your equation, your Newton's second law equation for F net. The left hand side is going to be the side that, or the forces from the diagram that are battling with each other, and that's what we did, and that could lead us to solving for one of the unknown forces, like the normal force here. It might, if we have the normal force, if we have a gravity force and we need to know acceleration, we could figure out what the acceleration was, stuff like that. So I'll end it there. I know this was long, but you really need to see some examples before you can go on your own, and you can always pause and go back and rewatch pieces and parts of this as you do other worksheets. So please always give me an email or something to let me know. Stop in to the office hours on Tuesdays and Wednesdays. Ask questions, shoot me questions. This is not bad after you've done some examples, but it just takes a few reps through stuff like this to get used to it.